going to talk about atomic orbitals. All right, back to atomic orbitals. And so something that you might remember, and hopefully you do from General Chemistry 1, was that originally electrons were thought of as particles only, but it was discovered that they also have wave-like properties. And in fact, everything has the particle, or all particles have a wave-like property. And you would have learned that when you discussed de Broglie wavelength. However, electrons, since they're so small, we have to take into account both their particle properties and their wave-like properties. And so the solution to the wave equations for electrons provides us with the visual representation of where an electron can be found 90% of the time. And that gives us something called, or gives us some regions of space that we call atomic orbitals. And we have some atomic orbitals drawn here. And you need to know the shapes of these orbitals. This is an S orbital, S for sphere. It has a spherical shape. And all three of these are p orbitals. So sometimes my students will say P for propeller or peanut, or a lot of people say it looks like a dumbbell. But you see that in the S orbital, it's completely spherical. And what this sphere represents is where we would find the 90% probability of finding an electron, or where we would find an electron 90% of the time. And what's interesting about a p orbital is that you see it has two lobes to it. It has this red lobe here, and then it has this blue lobe here. I don't want you to think that one of them means, there's an electron found in one and no electron density in the other. The electron in the p orbital can be found anywhere in here and anywhere in here. But what you should understand is that there's a region in between that we call a node. And this is a node, and this is a node, and this is a node. And where there is a node, that is a region where there is no probability of finding an electron. And again, you've got to be able to identify S and p orbitals by their shapes. The orbital, again, is a region where there is a calculated 90% probability of finding an electron. If you have electrons with the same energy level, they're called degenerate orbitals. That doesn't mean that they've committed a crime or anything like that. But let's say you have a 2px orbital, a 2py orbital, and a 2pz orbital. Those would be considered degenerate orbitals. They have the same energy. You also need to know how to construct electron configurations. In fact, we looked over them this morning briefly when we looked at the electron configuration of carbon, nitrogen, and oxygen, respectively. You should know the Aufbau principle, or the building up principle. What that means is you always start with 1s. Then after 1s is full, then you go to 2s. Once 2s is full, then you go to 2p, and so on and so forth. You don't just start at 2s, or you don't just start at 3d. The Aufbau principle means you start at the lowest energy levels, and then you build up. The next principle you need to know is the Pauli exclusion principle. And that states that orbitals will have the maximum amount of electrons with unpaired spins. The Pauli exclusion principle is not that. Sorry, that's Hund's rule. The Pauli exclusion principle, rather, states that if you have two electrons in the same orbital, they must have opposite spin. And the way that we represent that is, let's say you have a 1s orbital. We'll say that one electron is spinning one way and the other electron is spinning the other way. The last one, which I got ahead of myself on, was Hund's rule. And Hund's rule means that you want to have the maximum amount of electrons with unpaired spins in degenerate orbitals. Put another way, let's say you have three 2p orbitals. Let's say you have a 2px, a 2py, and a 2pz. When you start putting electrons in, you'll put one here. But if you have a 2p2, you don't put the next electron and pair it up like that. You don't do that. The next electron goes into the next available orbital, and so on. You only start doubling up electrons once each orbital has one electron in it. And thus, if we had 2p4, then you can start pairing up electrons. Hund's rule. So make sure you know those three rules. the Aufbau principle, or the building up principle, the Pauli exclusion principle, which states that if you have two electrons in the same orbital, they must have opposite spins, and Hund's rule. Sometimes I call that the bus rule. Like, let's imagine you're on the bus, okay, or you're getting on the bus, and there's a person sitting alone in a seat, and you are over here, and you want to get on the bus. You walk onto the bus. Would you sit next to the person who's all alone? No, that would be creepy, okay? You would go to the next available seat, then the next person would go to the next available seat. It's only once all the seats are half filled that you get on, you're like, well, I guess I got to sit next to someone. So you'd go, and then you start doubling up. All right. Anyhow, moving on to valence bond theory. When we have a bond, it results from the overlap of those atomic orbitals, the s orbitals and the p orbitals. Overlapping orbitals are like overlapping waves. And if you've studied physics at all, you have probably a pretty good idea of what I'm talking about. When you have constructive interference, this results in a bond, whereas if you have destructive interference, that results in a node. Now, you have to know how to define a bond according to this theory. And you also have to understand the difference between a sigma bond and a pi bond. If we take two hydrogen atoms, you have a hydrogen that has an unpaired electron and another hydrogen with an unpaired electron. When they come together to make a bond, that first bond, or the first bond between any two atoms, is called a sigma bond. So we have a sigma bond here. Anything after a sigma bond, if you have a double bond, the second bond is considered a pi bond. So sigma bonds. What's interesting about a sigma bond is if you take a cross section of a sigma bond, you get something that's symmetrical. So you get something that's symmetrical like this, okay, between the two electrons. And what you need to also understand is that in a sigma bond, the electrons spend most of their time in the overlapping atomic orbital space, right? Even though there is some electron density up here and here, they spend most of their time between the two atoms, where I have this circular cross section. Again, going back to the pi bond, I'll just cover this quickly here. A common example of a compound that you would have seen with, or a molecule with a pi bond would be nitrogen, okay, N2. This is the Lewis structure for nitrogen. Here, I'll just zoom in a little bit. Remember, the first bond between any two atoms is a sigma bond. Anything after that is a pi bond. So this is a pi bond, and this is a pi bond. So we have pi bonds. And pi bonds are the result of side-to-side overlap of p orbitals. So if you have a p orbital back here, and so if you have a p orbital, where was I? If you have nitrogen, okay, like this, okay, we have the sigma, and then we have the two pi bonds like this. When you have a p orbital and another p orbital, and they get close enough so that they overlap each other, so I'll see if I can select just this one. When they overlap like this, that makes a pi bond. All right, and pi bonds are weaker than sigma bonds. So we can scribble that down here too. Pi bond is weaker than a sigma bond. Molecular orbital theory, there isn't much that you need to know about molecular orbital theory because this is discussed in greater detail in organic chemistry too. However, you should know the idea of a bonding molecular orbital and an anti-bonding molecular orbital. So if you follow along with me here, it says atomic orbital wave functions can overlap to form the molecular orbitals that extend over the entire molecule. And so if we're talking about orbitals that extend over an entire large molecule, you can imagine that they get very complex. And thus, we'll only be thinking about something that is very simple. For example, if you look at a hydrogen molecule being formed, you have the hydrogen atom here with one electron, then you have the hydrogen atom here with one electron. When they overlap, they form a bonding molecular orbital, but they can overlap destructively and form an antibonding molecular orbital, which has a node where there's no electron density between these two lobes. So molecular orbitals are nothing more than a more complete analysis of bonds because they include both the constructive and destructive interference. You saw here that I took two atomic orbitals. This here is an atomic orbital, the 1s. This is also an atomic orbital, this 1s. Well, I have two atomic orbitals, and I end up with 1, 2 molecular orbitals. So I have the bonding molecular orbital and the antibonding molecular orbital. And thus, the number of MOs for any molecule is going to be equal to the number of atomic orbitals that were used to create those molecular orbitals. The antibonding molecular orbital is higher energy because it has a node. And when the atomic orbitals overlap, the electrons are going to go into the bonding molecular orbital rather than the antibonding. Why? Because they want to achieve a lower energy state. Again, you don't need to know much more about molecular orbital theory than this because it is largely covered in organic chemistry 2, and we use it very rarely, if at all, in organic chemistry 1 to take a look at a reaction. And thus, I won't be asking you any questions about molecular orbital theory. I would think the only thing that I would really need you to know is that when we have molecular orbitals, we can have antibonding and bonding. Antibonding is higher energy than a bonding. The number of molecular orbitals is equal to the number of atomic orbitals. And the electrons are always going to seek to go into the lower energy or the bonding molecular orbitals rather than an antibonding molecular orbital. Well, from that brings us to a section on hybridized atomic orbitals. And this is where we start covering things like Sp, so you would have learned this in general chemistry, Sp, Sp2, and Sp3 hybrid orbitals. These are very important in organic chemistry. They do come up a lot in this class. If we take a look at the ground state electron configuration of carbon, it does not explain why we get 4 bonds. Hopefully everybody can write down carbon is 1s2, 2s2, 2p2. So we have 4 valence electrons. 4 valence electrons means 4 bonds, right, Mr. Dion? Well, if you look at the atomic orbitals, we have the 1s that's full, we have the 2s that's full, but then we only have 2 unpaired electrons in the 2p. 2 of the 3 2p orbitals. Well, that would mean that the carbon can only make 2 bonds. That is not what's happening. Carbon makes 4 bonds, not 2 bonds. Well, then how does it do that? The answer is, as is shown here on the slide. What happens is one of the electrons gets excited from the 2s to a 2p. And when it gets promoted into that 2p, now we have 1, 2, 3, 4 unpaired electrons. 4 unpaired electrons means that the carbon can make 4 bonds. Well, yes and no, because we do have 4 unpaired electrons here. However, they are not degenerate. They are not all equal energy. And so how would we make 4 even bonds that spread out in the tetrahedral arrangement that we see with carbon? And the answer is you have to take those 3 orbitals, the 3 2p orbitals plus the 1 2s orbital, and you mix them together or hybridize them to make 4 degenerate sp3 orbitals with 1, 2, 3, 4 electrons. 1 unpaired electron in each orbital. Why is it called an sp3? Because it's made from 1s and 3 p's, hence sp3. And now we have a carbon atom with 4 unpaired electrons in degenerate orbitals, meaning they're all of equal energy. And that is why we can draw the Lewis structure of carbon as such, where it has 4 unpaired electrons surrounding it. Here I have it shown in the slide, showing the hybridization of the 3 2p orbitals and the 1 2s orbital to make 4 degenerate or equal energy sp3 orbitals. And hence, the carbon can form 4 bonds. Again, here's the Lewis structure of our carbon atom. 1, 2, 3, 4 unpaired electrons. And there, that helps us explain why carbon, when it has 4 single bonds, it adopts a tetrahedral molecular geometry. Now, what does a hybrid orbital look like? We saw a few slides ago that a p orbital just looked like this. We had a lobe like this and a lobe like this. We shaded one, we shaded the other one like that. Okay, well, that's a p orbital. And if you're wondering what a sp3 orbital looks like, it looks pretty close to a p orbital, doesn't it? This is an sp3 orbital shown on a carbon atom. You can see that one lobe is bigger than the other, and that is just a result of the mixing of an s orbital, which is smaller than the p orbitals. But I'll tell you something right now, is that when we draw an sp3 hybrid orbital in organic chemistry, I generally don't draw it the way it is shown here. Here's what I'll do. I'll draw the carbon atom, and I'll just draw one lobe, and I'll label it as being sp3. And that way the reader knows that it's sp3. If you're wondering, why do you label it, Mr. Dion? Because what you're going to see in a few slides is that when we have an sp2 orbital, it looks the exact same, except we write sp2. And when we have an sp hybrid orbital, we do the same thing, except now we write sp in it. And so in order to make CH4, which is methane, and in fact, it is the simplest possible organic molecule, excuse me, you have the 1s orbitals of the 4 hydrogen atoms overlapping with each of the 4 sp3 hybrid orbitals. If we zoom into the carbon here, we see that this is an sp3 hybrid orbital. Maybe I'll use my blue pen here. This is sp3, this is sp3, this is sp3, and this is sp3. Again, all we're representing is the carbon with 1, 2, 3, 4 electrons. 1, 2, 3, 4 electrons. And so as we take those hydrogen atoms that are all just a plain old 1s orbital that doesn't have to be hybridized, the 1s orbitals approach the sp3 orbitals and they overlap with them. And when they overlap, they make bonds. And so what I'm circling in yellow here, 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 and here, those all represent the sharing of the 2 electrons, one coming from the hydrogen 1s orbital, and one from each of the 4 sp3 hybrid orbitals on the carbon, and I make 4 sigma bonds. So this is a sigma bond, this is a sigma bond, this is a sigma bond, and this is a sigma bond. And you should remember from general chemistry that when I have 4 regions of electron density surrounding an atom, what's the furthest that they can get away from each other? The answer is that they adopt a bond angle of 109.5 degrees. And that is why when carbon is surrounded by 4 single bonds, we get a tetrahedral molecular geometry. So I'll put here methane CH4, and I'm going to put in brackets here that it is tetrahedral, like that. So tetrahedral molecular geometry. If we go to ethylene, we see that the carbon atoms are not sp3 hybridized. Rather, this time, they're sp hybridized. Well, why would they have a different hybridization in this molecule? If we draw the structure of ethylene, we see the reason why. It's because the carbon atoms are not surrounded by 4 sigma bonds, but now they're surrounded by 1, 2, 3 sigma bonds each, but they're both surrounded by a pi bond. The sigma bonds are the result of the overlap between a hybrid orbital with a hydrogen or a carbon. But the pi bonds always come from non-hybridized orbitals. In fact, it's always a non-hybridized p orbital, because I told you that the pi bond comes from the side-to-side overlap of p orbitals. In fact, I drew it somewhere back here. I'm trying to find it. Right here. A p orbital unhybridized. When it overlaps side to side, it makes a pi bond. Let's go back. If we look at the electron configuration for carbon, it's still 1s2, 2s2, 2p2. That's what's shown here. If we take, or sorry, it's not what's shown here. If we take one electron from the 2s2 and we move it over into a 2p, then we have 4 unpaired electrons. However, I only need to hybridize 3 of them because I'm only making 1, 2, 3 sigma bonds. And so I mix one of the s's, or the 1s, the 1, 2s orbital, with 2 of the 2p's to make 3 degenerate sp2 orbitals, and I leave one of them by itself. That's the one that I use to make the pi bond. It's in the 2p orbital, but again, it's unhybridized. So these are the ones that are used to make the sigma bonds, and this one is used to make the pi bond. What does that sp2 hybridized carbon look like? It looks like this. You don't see the carbon atom in here, but I'll draw it in for you. So here's my carbon atom. It should be surrounded by 3 sp2 orbitals. I have 1, 2, 3 sp2 orbitals. They each have an unpaired electron in them, right? My 1, 2, 3 sp2s with 1, 2, 3 electrons. And then I have a 2p that's unhybridized. Well, that's this right here. This is my 2p orbital, and it's not hybridized. Again, the sp2, I draw it in the same way you draw the sp3. It's just to make our lives easier. All we do is we write a lobe like this, and you can just label it sp2 as they've done here for each one of them. We don't draw the other part of the lobe just because it makes things too ugly, really, when you draw it. It just doesn't look pretty, and so we leave it out. The sp2 has 33% s character and 66% p character because it's made from 2 p's and only 1 s. Well, if you take 2 carbon atoms that look like this and you bring them close together, what you end up with is something like this. Again, all we're doing is taking 2 of these and bringing them together. And what happens is one of the sp2 hybrid orbitals from one of the carbons and one from the other carbon is going to overlap to make a sigma bond. Now what we're showing here is ethylene, which is a very simple organic molecule. It's this molecule here. In fact, we drew it earlier today. Anyhow, so you see we have the sigma bonds between the carbons and the hydrogens. 2 sigma bonds over here. So sigma, 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 sigma. However, there is 1 pi bond. Now this is where it can get a little frustrating for students because I told you that a pi bond was the result of the side-to-side overlap of 2p orbitals. They're overlapping like this. I don't know about you, but it doesn't look like these 2p orbitals are overlapping, does it? No, it doesn't look that way. I know it can be annoying. So what we do, and if you're wondering, well, why don't they draw them touching, Mr. Dion? It's because it looks kind of cumbersome. And if you're like, is that the reason? Yes, that's it, man. That's all there is to it. It just gets a little ugly. And so what I do to show my students that these orbitals are actually touching is I draw a little line between them. And this represents the overlap, and this represents the pi bond being formed. Remember that with the pi bond, you have electron density above, and you have electron density below the carbon atom. But remember, there's a node in between the two. All right, the 2 lobes that are overlapping. So there's our pi bond. Again, this is a better representation because you can see the actual overlap of the orbitals. It's not great, but it's better than it was on the last slide. Again, the only reason we don't draw it that way is because once you put in all the orbitals, they tend to overlap and it just gets kind of ugly. But this is the same thing, okay? It's just a representation of the ethylene molecule, nothing more than that. You know, something I didn't skip, but if we go back here, this is something that is just back here, is the bond angles. And we're going to talk more about molecular geometry later on. But if I have 3 regions of electron density, 2 sigma bonds, and 1 double bond, which counts as a region of electron density, if I want those 3 things to spread out as far as possible, they're going to adopt bond angles of around 120 degrees. You see, this is around 120, and this one's also close to 120. You don't have to memorize 121 and 118. As long as you say, Mr. Dion, I know this bond angle is about 120. That's perfect with me. This bond angle is about 120. Good enough for Mr. Dion. And good enough for our textbook. All right, with all that information in mind, let's see if we can try a practice problem. Let's see if we can draw the structure of formaldehyde. We're going to identify the types of bonds that form the carbon-oxygen double bond, and we're going to identify the types of orbitals in each carbon-hydrogen bond, and identify the atomic orbitals that the lone pairs are occupying. First thing we need for formaldehyde is a formula, which is CH2O. If we tally up the total number of valence electrons, we have 4 from the carbon, 1 from each hydrogen, but there's 2 of them, so plus 2, plus 6 from the oxygens, that gives us 12 valence electrons. And so when we put that together in a Lewis structure, we get something that looks like this. And this is our Lewis structure for formaldehyde. Could anybody tell me how many sigma bonds there are in formaldehyde? How many total sigma bonds are there in formaldehyde? And again, it's not a trick question.
3.
Yeah, absolutely. Yeah, 3 sigma bonds. So we've got 1, 2, 3 sigmas, and thus the last bond must be a pi bond. So we have 3 sigmas and 1 pi. We're not really worried about the hybridization of the hydrogens because hydrogen only ever forms 1 bond. And so it just has, this is a 1s1, and this is a 1s1. But what about the hybridization of the carbon and the oxygen? Let's start with the carbon. The carbon, if we just look at the valence electrons, you get 2s and 2p, 2s2, 2p2, but the carbon has a total of 3 bonds. So in order to form 3 bonds, that means you have to have 3 unpaired electrons. And so what we're going to do is we're going to excite one of the 2s electrons into one of the 2p's. So let's do that. Then we've got 1 in the 2s, and we've got 1, 2, 3 in the 2p's, which is good because now we can form 4 bonds. However, we need to form 3 sigma bonds and 1 pi bond. So how many bonds do we need to hybridize? All 4, 3, 2, who can give me a number? How many bonds do we need to hybridize? Anybody? How many would we need to hybridize? Exactly. Thanks, Clinton. We need to hybridize 3 of them. 1, 2, 3 to make 3 degenerate sp2 orbitals, and then we've got a 2p left over. So we've got 1, 2, 3, and then we've got a 2p left over like that. That's our carbon. And so if we draw the carbon atom, it's going to have 1, 2, 3. These are all sp2s, sp2, sp2, like that. Each one of these has an electron in it. 1, 2, 3, like that. And then it has an unhybridized p orbital. I'll draw it like this. We'll put the blue lobe like this, the red lobe like that. So that's our 2p. And there's 1 electron in that as well. Okay. Now what about our oxygen? Well, our oxygen, and I'm kind of running out of space here, but our oxygen is going to look like this. I'll go a little bit quicker here. For our oxygen, we've got 2s2, 2p, 4. So that would look like 2s, 1, 2, 2p, 1, 2, 3, 4. So I've got 2 unpaired electrons, and I need to make 1 bond. But I also need to make, 1 sigma bond and 1 pi bond. However, I can't just leave it unhybridized because then they won't spread out evenly. And so I need to hybridize these orbitals. So what I'm going to do is I will hybridize, and I'll make 3 degenerate sp2 orbitals and have 1, 2p. Why? Because there's a pi bond attached to the oxygen. And now I've got my 6 electrons. So 1, 2, 3, 4, 5, 6. And thus these two pairs will be the lone pairs. This one is the one that's used for the sigma bond, and then this one is used for the, for the pi bond, the unhybridized one, pi bond. And so now, and I'll draw in the hydrogens here. So here's a hydrogen, here's a hydrogen. So hydrogen, hydrogen, they're both 1s. And now I'm gonna have to move this thing a little bit. So I'll move it down here. And now I'm gonna try my best to draw my oxygen, which is gonna look like this. It's got one sp2 orbital, two sp2 orbitals, three sp2 orbitals. So I'll put sp2, sp2, sp2. I'll put a lone pair here, a lone pair here, an unpaired electron here, and then I'll put the 2p orbital here and here. And so what's going to happen is the oxygen is going to come close to the carbon so that the two sp2 orbitals overlap. And now I've made a sigma bond between the two. I can show the overlap of the lobes of the p orbitals to make the pi bond. So this is my pi bond. This is a sigma. This is a sigma bond. This is a sigma. And this is a lone pair. And this is a lone pair. And so the types of bonds that form the carbon-oxygen double bond are a sigma and a pi. The atomic orbitals that have formed each carbon-hydrogen bond are the sp2 from the carbon and a 1s from the hydrogen. And what type of atomic orbitals are the lone pairs in? You can see that each lone pair is in an sp2 hybridized orbital. And so we'll put sp2 for each of those. And there we go, a little bit about hybridization. So we've covered sp2 hybridization and sp3 hybridization. If we have a triple bond, and I'll go over this a little bit quicker, it's much the same thing, except now you've got two pi's, and the carbon would have two sigmas attached to it. And so we only need to hybridize two orbitals to make two degenerate sp orbitals when a carbon has a triple bond on it. And so we have two unhybridized 2p orbitals to make two pi bonds. So two pi bonds, like that. All right, and so this is what it would look like if you drew an orbital overlap diagram of this molecule, which is called acetylene. You have two pi bonds, one here and one here. You have a sigma bond in the middle. Maybe I'll highlight that in green. So you have one of these, and you have two of these. And then you have a sigma here. So this is a sigma, this sigma. And then this is a sigma here, like this sigma. If you're confused at all and you want me to give you the quick and dirty answer to all of this, the answer is this. If you have a carbon that's surrounded by 4 single bonds, it's sp3 hybridized. If you have a carbon surrounded by 2 single bonds and a double bond, it's sp2 hybridized. And if you have a carbon surrounded by a triple bond and a single, it's sp hybridized. Done. There you go. You should understand the theory behind hybridization, but that is the summary in a nutshell. Let's take a look at this compound, nematine. It's first isolated from the fungi shown here. However, its structure was not verified until recently. Determine the hybridization state of each carbon atom in nematine. Let me start with this one that I'm highlighting in yellow. If I highlight these 4 in yellow, could anybody tell me what the hybridizations of the 4 carbons in yellow would be? I'll give you a clue, they're all identical. Anybody?
SP.
Yeah, absolutely, they're all sp. Is there another carbon in there that's sp? There actually is. This one here would also be considered sp because it's surrounded by 2 sigmas and 2 pi's. So all the ones that are sp hybridized here, and you can put it like this. This would also be sp, 2 double bonds. What about sp2s? If I was to highlight these ones in green, would you say that these are sp3 or sp2? The ones that I have highlighted in green. Would they be sp2 or s? Yeah, thanks, Guyana. Absolutely. The ones I have in green are sp2. And then that leaves us with a few more that are left over, but all the ones that have 4 single bonds, those are sp3. And so there you go. We were able to identify the hybridizations of these carbons very quickly. We didn't have to do a complex treatment of orbitals. If we saw 4 sigma bonds, if we saw 4 sigma bonds, we knew it was sp3. If we saw 3 sigma and 1 pi, we knew it was sp2. And if we saw 2 sigma and 2 pi, then we knew it was sp, just like I have shown on the far left. We figured that out very quickly. Well, if you're wondering what the relationship between bond length and strength and hybridization is, I have that summarized on this slide right here. This is something that always comes up in organic chemistry. It's a question that comes up on ACS finals, for example. Or if anybody who's listening is interested in taking an MCAT exam, an MCAT for medical school, or the DAT for dental school, it's kind of question that they love to ask is, how do you compare bond length and strength with hybridization? And the answer is shown here. You can see that as you go from a carbon that is sp3 to sp2 to sp hybridized carbon-carbon bonds, they get shorter and shorter. You go from 1.54 to 1.34 to 1.2 angstroms. Why do they decrease in length? It's because as you have more orbitals overlapping, the atoms have to get closer and closer. However, you can imagine that we have a reverse trend in terms of numbers and bond energy. If we have more and more bonds overlapping, the bonds actually get stronger and stronger. So as we go from a single to a double, it doesn't double in strength entirely, but it's close to double in strength. And then it increases much more from there, right? It increases a lot. You know, the numbers that I can give you that I think are really quick and easy to remember are kind of a 400, 600, 800 kilojoules per mole roughly, as you go from a single carbon-carbon bond to a double carbon-carbon bond to a triple carbon-carbon bond. These are just numbers that are kind of handy to have in your back pocket sort of thing. All right, let's try another practice problem. Question 1.26 says, rank the indicated bonds in terms of their increasing bond length. So let's do, if I call this bond A, I call this B, and I call this one C, we'll put here shortest, and then we'll put over here longest. Could anybody tell me which one of these bonds, A, B, or C, would be the shortest bond? And again, it's not a trick question. Would never try to fool you. Yeah, thanks. Andrew, Nicole, Kiana, everybody's right. Absolutely. Oops. Didn't mean to do that. The shortest would be C. Which one would be the longest? Yes, absolutely. The longest one would be A. Absolutely. And then that means that B is going to be somewhere in the middle. So we'll put it there, somewhere in the middle. Let's rank them in terms, it's not even on here. Let's do it for fun. Let's do strength. We'll put here bond strength. So we'll put here strongest, and weakest. Which one would be the strongest, A, B, or C? Anybody? Yeah, absolutely. C would be the strongest. Yep, A would be the weakest, and B is somewhere in the middle. Okay, what time is it? 10:51. Let's see here. What's next? Molecular geometry. So next we got molecular geometry. Then we have dipoles, intermolecular forces, and solubility. So we have a few sections left. why don't we just talk about molecular geometry and then we'll call it a day. Again, I mentioned this at the very beginning of the class. You don't need to know every molecular geometry that you would have learned in general chemistry. You only need to know linear, bent, trigonal planar, trigonal pyramidal, tetrahedral. You know, those are the main ones that come up in organic chemistry. But you do have to know a little bit about valence shell electron pair repulsion theory. What do we know is that when we have pairs of electrons, whether they're shared in a bond or if they're lone pairs, we know that they don't want to be anywhere near each other. They want to repel each other. And so in order to determine how they spread apart from each other and the shape that they develop or the molecular geometry that they develop, we have to look at what's called the steric number. A steric number is just a look at the number of sigma or pi bonds and lone pairs of electrons. So if we have methane, for example, you can see that it has 4 sigma bonds, no lone pairs. So we say that it has a steric number. Steric number is equal to 4. If we go to ammonia, it has 3 sigma bonds and 1 lone pair. So it also has a steric number of 4. And water also has a steric number of 4. It has 2 sigma bonds and 2 lone pairs. However, even though all 4 of these have the same steric number, they don't have the same molecular geometry. What they do share in common is the electron geometry, not their molecular geometry. Just skipping ahead here and thinking about steric number and hybridization. Hybridization and steric number. If the steric number is 4, then the hybridization of your central atom is Sp3. If the steric number is 3, it's Sp2. And if the steric number is 2, it's Sp. And thus, since the carbon, nitrogen, and oxygen, and methane, ammonia, and water all have the same steric number, they are all Sp3 hybridized. The carbon is Sp3, the nitrogen is Sp3, and this oxygen is Sp3. Well, for any Sp3 hybridized atom, the 4 valence electron pairs, whether it's in a bond or a lone pair, are going to form a tetrahedral electron group geometry. That's what I refer to as electron geometry. Put another way, the electrons are going to spread as far apart from each other as possible, and the electron pairs, again, that includes bonds and lone pairs, are going to spread apart so that they adopt roughly a tetrahedral geometry. If you look at methane, which is CH4, you see that you have the carbon in the center here and the 4 hydrogen atoms, and they spread out to form not only a tetrahedral electron geometry, but also molecular geometry, because there are no lone pairs on the carbon. Each one of the bond angles is roughly is 109.5 degrees. Whereas if we go to ammonia, NH3, what happens is that the lone pair, since those electrons aren't shared, it tends to push the nitrogen-hydrogen bonds down slightly and closes up those bond angles a little bit so that they adopt a bond angle of about 107 degrees. And then in water, since you have 1, 2 lone pairs, it pushes the oxygen-hydrogen bonds even closer together and closes that gap up even more so that you have a lower bond angle, which is around 105 degrees. Again, for this course, as long as you know that all of the bond angles on this slide are close to 109.5 degrees, as long as you know that this bond angle is less than 109.5 degrees, and this bond angle is less than 109.5 degrees, that's good enough for me. And so you need to know the difference between electron geometry and molecular geometry. Here in the last column, we have molecular geometry, but over here we have arrangement of electron pairs. I like to refer to this as electron geometry. So if you go back to methane, CH4, it's got 4 sigma bonds, no lone pairs. Therefore, its molecular geometry and electron geometry are identical. Remember that the molecular geometry considers only the atoms or bonds, whereas electron geometry includes bonds and lone pairs. So we'll put here lone pairs plus bonds. So if we go to ammonia, you have one lone pair and 1, 2, 3 bonds. Therefore, its electron geometry is tetrahedral. However, molecular geometry only considers the 3 bonds, and therefore we say that it's trigonal pyramidal. If we go to water, water has 2 lone pairs and 2 bonds, which would give it a tetrahedral electron geometry. But again, the molecular geometry only considers the bonds, and so it is having, or it has, a bent molecular geometry. So make sure that you know the difference between molecular geometry and electron geometry. If you're wondering if I have this summarized anywhere, the answer is absolutely. Here is a summary of all the steric numbers, hybridizations, and their molecular geometries. We've already covered the tetrahedral with a steric number of 4, so something like methane, and the trigonal pyramidal with a steric number of 4, something like ammonia, and water, which has a steric number of 4 and is bent. Whereas if we have something that's trigonal planar, an example of that would be something like boron trifluoride. It would be trigonal planar. And something that's linear that you might have seen in general chemistry would be like beryllium hydride, BeH2. And again, so you need to know the difference between all these different molecular geometries and how they relate to steric number and hybridization. Well, with that in mind, let's try one more problem and then we'll call it a day. It asks us here to use Vesper theory to predict the geometry for each of the following structures. Whenever you see just geometry, what they mean is molecular geometry. So molecular geometry. Let's start with BH4. If we look at the boron, could anybody tell me the hybridization of that boron? It's got a negative charge. No trick questions. What's the hybridization of that boron? Thanks, Andrew. Absolutely. It's Sp3. That means it has a steric number equal to 4. That means that its electron geometry is tetrahedral. And since there's no lone pairs on the boron, that means its molecular geometry is also tetrahedral. Kind of running out of space here. Tetrahedral. Okay, and if you're wondering, where the hell are you getting that from? Well, let's go back here. We have the boron having a steric number of 4. It's Sp3 hybridized, and it has no lone pairs. Therefore, BH4 minus would fit in here as well, alongside CH4. So tetrahedral electron geometry and molecular geometry. And we could even practice drawing the compound, the ion. So to show the tetrahedron, we like to put one bond going in the back, and then one coming out front like this. And there you go. Now we've got BF3 over here. Who could tell me what the hybridization of the boron in BF3 is? Boron trifluoride. Again, no trick questions. What would the hybridization of this boron be? 3 sigma bonds, no lone pairs. Yeah, thanks, Clinton. Absolutely. It's Sp2 hybridized. Sp2. Perfect. If you're wondering, how did you figure that out? Well, I went over here. I said it's got a steric number that's equal to 3. 3 bonds, no lone pairs. So it's Sp2 hybridized. Now, if it's got no lone pairs, it must be trigonal planar. So that means that both its molecular geometry and electron geometry are trigonal planar. So we'll just leave it like that. Could anybody tell me what the bond angle would be, or the bond angles would be in BF3? Again, not a trick question. There are no trick questions in Chemistry 3101. What would the bond angle be here? not 107. If I take a circle, right, this is a whole circle here, which is 360 degrees, but then I divide it by 3 equal pieces. Since they're spread out equally, I get 120 degrees. So every bond angle in here would be 120 degrees. All right. Here we go.